Hi apes! Today we're going to be looking at Unit 4, Part 3, which is going to focus entirely on Earth, so solid Earth here. So one thing that we should start with is just understanding our levels of the Earth, or our layers of the Earth. If you've taken geosystems, this might be something that you remember from there. But at its essence, we have three layers to our Earth. We have the core, which has solid and liquid. We have the mantle, which is again is a little bit of solid, little bit of fluid material. And then we have our crust, which is entirely solid. Okay, so our crust is up here. Now if you take a look at an apple, the crust is about as thick as an apple skin. So we're not talking about a huge component, but this is really all we know the most about for our Earth. Now I want to break our crust and our lithosphere, our crust and our mantle, down a little bit to give us two other layers to apply that to plate tectonics. So two important words here are our lithosphere and our astenosphere. So the lithosphere contains crust and a little bit of mantle. Now the key thing about the lithosphere is that it's all solid. So they are solid plates. So the lithosphere contains the entirety of the crust and a little bit of the upper mantle that's solid. The astenosphere is the semi-liquid mantle. So this has probably the consistency of about really, really hot toothpaste. Now the reason why this is important is because the astenosphere has convection currents that occur. So remember convection currents from our atmosphere. Here you have these very slow convection currents that occur in the astenosphere. And that allows for a little bit of flow, a little bit of movement in that astenosphere that we're going to see move our crust plates around. And that's going to set the stage for our theory of plate tectonics. So when we take a look at plate tectonics, one thing we have to recognize is that our Earth is divided into giant plates. So some of the major ones we can tell because we put names to the continents above them. So the North American plate, the African plate, South American plate. So the continents, as we know them today, have actually changed over time. So the picture on the right is showing you throughout time the location of our continents. Now there are several pieces of evidence that we have that helps to support how we know that our continents have moved throughout geologic history. So some of the big ones is the shape of the continents. If you take a look at this picture down here, you can see that this South America looks like it hugs right up against Africa and it kind of fits right in there. Here's Antarctica, here's Australia. So the shape of our continents at one point in time was one giant landmass. So we did have one giant landmass that we called Pangaea. And then Pangaea broke apart into two pieces, and then it continued to break apart into the shape that we know today. So one thing is the shape of the continents, that we know that they kind of fit together. Now another thing is that there are similar rock formations, similar mountains that cross continents. So you can connect to the age of rocks and the types of rocks across continents. And at one point in time they were together and then they were split apart. Another thing is similar fossils. So you might have fossils here in South America that match up time and species-wise with fossils in Africa. And you wouldn't be able to find the same fossils in the same period of time on two separate continents if they were split by an entire ocean. So our fossil records are giving us some signs that these continents at one point in time were together. The age of oceanic rocks is some very new stuff that has a lot of people very interested in this. So here you can see this red line that's going up through the middle of our Pacific Ocean. Here you can see it going down the Atlantic. So this is called our mid-ocean ridge. Now what's significant about this is that this rock is very young. This is very new rock, less than 100 million years old, when our planet is 4.6 billion years old. So our rocks are very, very young here, and that's giving us a sign that this is new rocks that's being formed. So along this mid-ocean ridge, that's what we refer to as a divergent boundary. So magma is able to come up from the astenosphere, and it hits that cool water and it hardens into brand new rock. Now, our oceans aren't getting bigger, our planet's not getting bigger. And so, what you can see is that as you move away from this mid ocean ridge, the rocks get older. So, what that's implying is that there's some type of movement that the further away you get from the mid ocean ridge, the older your rocks are. And then at some point, they get as old as they can in the ocean, and then they actually sink back into the asthenosphere and melt and start over. So, our age of our oceanic crust actually gives very compelling evidence that our Earth's crust, our ocean bottoms, are constantly being remade. Now, another thing we look at is the magnetic pattern in that rock. So when that rock forms, our magnetic pole is one way, but over time it's shifted throughout the years, and we see very predictable concentric patterns of our magnetic striations in rock based on the way the pole was oriented when that rock formed. And again, they're very concentric from outside of that divergent boundary. So these are all really strong pieces of evidence that support this really strong theory in earth science of plate tectonics. So we do have mechanisms for how these plates move. They'll either move divergent, convergent, or transform. So at the divergent boundary, we call that a spreading center. So this really is our mid-ocean ridge. We have one giant divergent boundary on our planet. So here, two plates are moving away from each other, and when that occurs within the asthenosphere, magma comes up to replace that rock and hardens and forms new rock. So this is where we have that brand new rock forming. But like I said, if you're forming new rock, we have to destroy rock at another place, and that occurs at a convergent boundary. So here at a convergent boundary, we actually have two options. If you have an oceanic plate involved, the oceanic plates are very dense, and so an oceanic plate is going to sink below another plate, and that's called subduction. So here we have an oceanic plate that might be hitting up against a continental plate. And what happens is that very dense oceanic plate is going to be forced back down into the asthenosphere, is going to subduct, it's going to melt, and it's going to become part of the asthenosphere again. Now, if you have two plates that come together or at a convergent boundary on land, one plate is not going to be more dense than the other. So instead, what you might see are mountains form, because they come together and then they press upwards. Now, the other type of boundary, which is actually one of the least common of our boundaries, but probably the one we hear the most about, is transform. And so those are the ones that slide past each other. This is like our San Andreas Fault in California. Now, one key thing is that all three of these can form earthquakes, and actually our strongest ones occur at convergent boundaries. Transform we have in our like San Francisco, but the earthquake in Japan that caused that tsunami, that was because of a convergent boundary. And divergent boundaries, we actually do have lots of little mini earthquakes that occur all along that mid-ocean ridge. Now, I want to talk about soils. So this is my favorite little soil guy here. So soils, we're going to get into a couple of vocabulary words first. So one thing that I need you guys to understand is the difference between weathering and erosion. So weathering, a good definition of weathering is the chemical and physical breakdown of rock. Now the physical weathering just breaks it into smaller pieces. It has its same chemical components to it. So physical weathering just breaks it into smaller rocks. But chemical might actually change it. So here you might wear away the rock, you might oxidize it, so oxygen, rain, carbon dioxide. There's different plants that will put out acids that can dissolve away the rock. So chemical weathering actually changes the components. And we also will throw in biological, because sometimes you can have trees that will grow through rock. And you sometimes see this on sidewalks in older neighborhoods, that they're buckled because tree roots have grown, so it applies a lot of constant pressure. So you might even have some biological that will do some physical weathering. Now here's another example of physical weathering, which is frost wedging. That when water, this is like why we form our potholes in our winter. So when water gets into cracks in the street, you have the water in there, When it freezes, water expands, and that can expand to the point where it can break rock. Now this often gets confused with the word erosion, but erosion really is the movement of rock that might have been weathered, or it's the movement of soil. So erosion is the movement of soil and rock, and this tends to be caused by wind, water, and even ice if we're talking about glaciers. It can also be caused by living organisms. Living organisms can stir up and loosen up that soil and lead it to erosion. Now, the reason why we are concerned about erosion is because there's a loss of topsoil. So we're going to learn about in our agriculture unit how important soil is and what an important resource it is. But when we allow erosion to occur, we will lose that really, really important resource. And another thing to consider is that if you lose it in one area, it's going to get deposited in another. And a lot of times if it gets deposited in waterways, it's going to be carrying contaminants with it, nutrients with it, which will lead to problems, and also change the water quality and make it more cloudy, which is what we refer to as turbidity. Now it is important that we understand our soil layers. This is something that's called a soil profile. So when soil forms, it actually takes a very, very long time for soil to form. Now when soil forms, we actually start down here at the rock. Okay, so we call this our R horizon or our bedrock. So this is the parent material that you start with. So the first stage of soil formation is actually to weather that material away. So we have broken up rock. Now once you have some weathered material here, you might have some moss or some lichen that can start to grow on that and help with that weathering, and dye and add some organic components to it. So we're actually going to hop up the next thing that forms. So here's the first layer, here's the second. The next thing that forms is our O horizon, or our organic material. Now sometimes you might see this referred to as humus, which is different than humus. So this is humus, which is partially decomposed plant material. Now this isn't going to be enough to support large plants, so what then forms is our A horizon, which is the topsoil. So our A horizon forms, and that's going to start to build up more and more organic material. So we have organics from stuff dying, and we have minerals from our our parent material here. The next thing that forms is our B horizon, or our subsoil. So here, what happens here is we call this the zone of accumulation. So as water starts to percolate down through here, it's going to build up minerals, clays, in our B horizon. So this is a collection zone. Now, last and not always, you might see an E horizon. So that E horizon is a zone of eluviation. Eluviation is a synonym for leaching. And so leaching is when water percolates or moves down through the soil and it pulls out the nutrients and it lowers it to that B horizon. So our E horizon is going to tend to have no nutrients in it. So you tend to not see roots grow into your E horizon because there's no reason to. This is kind of like a path through. But that E horizon doesn't always form. Now here's just a picture so you can see. You do see color changes as you go down into the depths of your soil. So this is a picture that a student had given me from a project they were doing in her yard. But just so you can see that you do see color changes because of the mineral changes in the content of the soil. So like I said as we were going over that, some of the things that affect whether or not soil can form, one of the biggest is time. It takes a very, very long time for soil to form. One of the big drivers here is climate. You need to have weathering occur, you need to have leaching occur to have that movement of those minerals. So if you're very dry, if you're very cold, you're not going to have your soil form very fast. And that's why areas like tundra are very sensitive, because their soil, they're very vulnerable if they have erosion, because it's going to take a very long time to form any new type of soil. Another key thing is that parent material. What type of rock are you starting with? What type of minerals are you starting with? The topography is going to be important. How the land looks, because this is going to affect the drainage patterns. Are you in an area that has a lot of runoff, Are you in an area that has a lot of erosion? Are you in an area that collects a lot or that is deposited? So the topography is is important, as well as living organisms. How many critters are there to help break down materials and form that humus in that organic layer? Now, soil types, we tend to associate that with size. So sand, silt, and clay are our primary soil types. Now, you don't have to memorize the sizes that are over here, but you do have to know that sand is the biggest, silt is in the middle, and clay is the smallest. So with sand being the biggest particle size, what that means is water moves through it really, really easily. Now, what that means is that sand is not very good for farming because you need to have water in your soil so the plants can absorb it. So while sand has a lot of movement, it doesn't hold on to nutrients and it doesn't hold on to water. Hopping down to clay, clay is the smallest particle size, so that is very slow infiltration, but it holds on to water well and it holds on to nutrients. Now we have a lot of clay soil here in Virginia, and you might know this, that when we get really, really bad rains, water kind of pools on the surface because it takes so long for it to move through. Now silt is somewhere in the middle with medium infiltration and water. So this would be okay to farm in, but the best type of soil to farm in is actually what we call loam, which is an even distribution of all three size types. It's best to have a little bit of variety in your soil size particles, because even if they're silt, if they're medium size, if they are all the same size, they'll kind of form a matrix that makes it even, that makes it hard for water and roots to move through. So the different types of soil properties, and we'll be taking a look at this in class, but one is texture, the size and composition, so you can actually come up with a name for your soil. How much water does it hold, or what we refer to as porosity, and that's tied to how much water and also nutrients, because remember, leaching is water moving through, so if you have a lot of water moving through, it's going to leach a lot of your nutrients out. Permeability, how easily does that water move through? How easily are roots able to move through? This is going to help you make decisions about irrigation. And then the chemical makeup, nutrients, pH. This is going to determine how much fertilizer you need. Do you need to put limestone on it to maybe raise your pH a little bit? If you're too acidic, you might add limestone. So farmers will take a look at all of these when they're making decisions about their soils. Now, what we're going to see is we're going to be able to determine our soil type based on how much clay, how much silt, and how much sand there is in it. So we'll do this using a soil triangle. So just to give you an example here, if I have a soil sample that, say, has 40% clay and 50% sand and 10% silt. I'm going to find here on the clay side, I'm going to use this side, I'm going to find 40, and I know I'm going to have to go across. On my silt side, I'm going to find my 10, and I'm going to follow that line down. And on my sand side, I'm going to use 50, and I'm going to follow it up. So there's just one spot on this triangle where all three of these lines meet, and that's right there in sandy clay. So we'll get some more practice with this, but you'll be able to take a look at a soil sample, and based on its clay, silt, and sand components, we'll be able to come up with a name for it.